What is the efficiency of the Carnot cycle? Well, the formula that we showed on the key concepts slide was that efficiency is equal to 1 minus the cold temperature rate as a ratio with the hot temperature. How do you get there? That's what I'm going to aim to show in this example. I do want to say that for this course, this example is going to entail more mathematical steps than I would generally expect in anything. We are going to be able to follow it though, because all of the formulas that are involved are things that we have seen before. But don't feel like you need to memorize any of this, or that you'd ever be asked to really do anything like what is shown in this example. So let's get it started here. We're starting by investigating the top isotherm. So in other words, a process going from 1 to 2, and that happens with the heat source in contact with the engine and maintaining that temperature. By the ideal gas law, pressure and volume would be inversely proportional, and when things are inversely proportional, you can stack those proportions. And in this case, that would mean if you have a P2 over P1, that should be equal to V1 over V2. In other words, the 2's and the 1's are kind of reversed on each side, the equal sign there. As well, we have the formula that we looked at earlier for the isothermal process for, you could either say it was for the heat or the work done by the system. It involved that natural log with a ratio of the two volumes. So V2 is the volume, of course, at 0.2, and V1 is the volume at 0.1. All the subscripts with 2's and 1's and all the other numbers I'm associating with the corresponding points in the PV diagram here. This process, since it's occurring at the hot temperature, that's why that's the appropriate temperature to include in this formula. So that's what we're going to put together with all this stuff later on. Now moving on to the adiabatic part from 2 to 3, the relationship that holds for adiabatic processes is shown here with the two, with kind of the initial point and the final point for this process. In other words, P2 V2 raised to the gamma should be equal to P3 V3 to the gamma, as we've seen when we looked at adiabatic processes. So we're just going to note that and hold it until we put this all together later on. Now looking at the bottom isotherm, we can collect a few more formulas similar to what we did with the top isotherm. Pressure and volume are inversely proportional following the ideal gas law, so that leads to this formula right here. And as well, we can use the formula for work and or heat. There are some subtleties with minus signs here. This is actually minus the work done going from 3 to 4 by this engine. And what that relates to is that you might notice that the ratio here in the natural log, if it had really been final volume over initial volume, should have been V4 over V3. So when I take the reciprocal of that, it turns out the natural log of a reciprocal is equal to the negative of the original. So that's kind of what reconciles the fact that there's this minus sign here. And this is set up to reconcile with the fact that QC represents the cooling of the engine. In other words, it is an outflow of heat for this process in the overall cycle. And then going from 4 back to 1, we have the adiabatic relationship that connects the pressures and volumes for points 4 and 1. And now we're going to take all those formulas, and here on this last page, we're going to combine all of them. And this is where there's really way too much math going on. It's all algebra. It's all being done. It's followable, but there's a lot of steps. And it talks about taking these adiabatic related formulas and dividing them to get some more stuff with ratios and exponents. And then we're going to use those formulas that came from how the ideal gas law describes an isothermal process, and use that to substitute for the two pressure ratios. And then some algebraic simplification happens that yields this formula, which then you can you basically have two ratios raised to the same power equal to each other. So you can just get rid of that power, and that leads to this simple relationship here, which was a lot of work to get to, but is amazingly simple once you get to it. That is the key thing right there, because then when you look at QH and QC and how they relate to these other two expressions, there are these natural logs of these two ratios, and it sure looks like things would be really neat if those natural logs were just equal to each other, and they are if the ratios inside them are equal to each other, which is what we just showed. And so that means that when you take the ratio of QC to QH, it has to be equivalent to TC over TH, which based on the result we had in the previous example that really said for any heat engine, the efficiency was equal to 1 minus the ratio of QC to QH. For the Carnot cycle, we've just shown that that ratio is equal to TC to TH, so therefore this yields the Carnot efficiency formula.